Dear students, welcome to lectures number 7 of computer graphics. In this lecture, we will discuss in detail the graphics or rendering pipeline. In computer graphic, it has many names like also known as computer graphics pipeline or rendering pipeline, or simply we can say it graphics pipeline. So we can define graphics pipeline as a conceptual model that describes what steps a graphics system needs to perform to render a 3D scene, natural scene to a 2D screen. So simply it is a process to convert a 3D natural scene into a 2D digital scene that we can see on our laptop, mobile, or any other viewing device. As far as the render is concerned, also called rendering process, to generate an image from a model by means of a software program. The model can be described in three-dimensional objects, and it would contain geometry, viewpoint, texture, lighting information, etc. The image that we see on our digital devices is a digital image or raster graphics image. Therefore, the term is an analogy with an artist rendering of a scene. Hence, rendering is mostly used in architectural design, video games and animated movies, simulators, TV special effects, and design visualization. The techniques and features used vary according to the project. Rendering helps to increase efficiency and to reduce cost in design. So dear student, let's start. Here is the outline of the lecture. The outline will be covered in 3 subsequent lectures. Lecture 7, the current lecture, and the 2 subsequent lectures, lecture 8 and lecture 9. In the beginning of the outline is the introduction that I have already given to you. Number 2 is rendering pipeline. This we will discuss in this specific lecture. Number 3 is vertex processing. Number 4, primitive processing. Number 5, fragment processing and summary. So these are the major areas that we will discuss in coming lectures. Hence, to begin, we will discuss rendering pipeline in this lecture in detail. Dear student, as I already told you and explained you the rendering process in the beginning of the lecture, here I will tell you that how rendering can be applicable. So it is a process of generating an image given, number 1, a virtual camera. The virtual camera is different from a digital camera that we use in our daily life. Basically, a virtual camera is a function of graphics or animated software like Maya or 3D Studio Max, etc. However, the virtual camera behave in the same way a camera or digital camera would in real world situations. The software like Maya 3D Max Studio containing virtual camera is made up from mathematical calculations that determine how the object will be rendered based on the location and angle of the virtual camera in the software program. It means, as with a real camera, when working with a virtual camera in 3D animated software programs, you can also use functions like pan, zoom, or change focus and focal points, etc. At second number, we have to deal with different kinds of objects which you can found in natural or synthetic image scene, and obviously the light sources, which plays an important role in generating different types of computer graphics. There are various techniques to perform rendering. Number 1 is rasterization, topic of this course that we discuss in this lecture. and number 2 ray tracing. This topic will be discussed in week 6. Hence, rendering is considered as one of the major research topics in computer graphics in terms of animation designing and geometry processing. The most important and famous technique for implementing rendering process is a rasterization. Rasterization is a rendering algorithm for generating 2D images from 3D scenes. There are numerous rendering algorithms based on the rasterization techniques which help to generate 2D images from 3D scenes. For example, digital differential analyzer and the most important Bresenham's algorithm. These algorithms are also part of this course and we will discuss them in detail in the later lectures. Coming back to our slide, the students, you can see that rasterization is also a process to transforming geometric primitives such as lines and polygons into raster image representation, that is pixels. Simply, we can say that rasterization is a process which represents an image in two-dimensional matrix where the intersection of row and column represents a pixel value or a pixel, also called picture element. Hence, symbolically, the whole process is known as raster scan or scan conversion. Students, if you focus on the slide, you can see a figure. The left side of the figure represents 3D scene, means the objects are in 3-dimensional format. All these objects are rendered using rasterization technique to a 2D screen image that you can see at the right side figure. Hence, to summarize this process altogether, we can say that 3D scene image rendered using rasterization technique into a 2D screen image. Dear student, I hope that you will understand the concept of rasterization in this slide. Rasterization also helps to process 3D objects representing in the form of various vertices, lines and polygons. All these primitives are processed to obtain a 2D image with the help of rasterization technique in the rendering process. The process is demonstrated in the slide, in the figure given on the slide. If you see the left side of the figure, you found a geometric shape of a kettle which is drawn with the help of lines, polygons and vertices to create 3D object shape. Whereas at the right side of the figure, you can view the 2D image of the kettle, which is based on the geometric model of the kettle. The 2D image is rendered after applying the technique of rasterization. At parallel, we can also add lighting and shading information on a 2D image. Hence, to summarize the process, we can say that any type of geometric shape or model can be rendered using the rasterization technique into a 2D image. Further, it is important to discuss the rendering pipeline incorporating rasterization. Here are some major artifacts for rendering pipeline. Number 1 artifact is processing stages comprise the rendering pipeline, also called graphics pipeline. Number 2 artifact is the support of graphics hardware, which normally we use for this purpose is GPU, graphical processing unit. The GPU will help to compute stages of rasterization based rendering pipeline. And number 3, the important artifact is the software interfaces like OpenGL and DirectX, etc. These softwares will act as bridge between processing stages and graphics hardware. One of the software interface, that is OpenGL, we will follow in this course for implementation of various graphical primitives in the later lectures. That is, we will cover this in the practical portion of this course. There are two major tasks of rendering pipeline. Number one is 3D input and number two is 2D output. These tasks are further divided into subtasks for finalizing the whole rendering process. First of all, we will discuss 3D input and its subtask. Number one subtask is the use of virtual camera, which is provided by different graphics software like Maya, 3D Studio Max, etc. in order to adjust position, orientation and focal length to get picture of the graphics object. Number two subtask is objects, which can be represented in the form of points, that is vertices or vertex, lines, polygons, or various type of geometric shapes or models. The third important subtask is light sources. This task is very important for objects in terms of direction, position, color, intensity. The concept of light on the object is discussed in detail in our previous lecture number 5. And the final subtask of 3D input is texture. This has already been discussed in detail in our lecture number 6, part 2. The second major task of rendering pipeline is 2D output, which represent per pixel color values in the frame buffer. All the pixel values are written into the frame buffer. The frame buffer further consists of various types of small buffers. That is, number one, the Z buffer, which store the pixel values that reflect the depth of the object on the image. Number two is stencil buffer, which store pixel values that reflects the shadows in the image. Number three is accumulation buffer, which stores the pixel values of blending. Blending is a process in computer graphics which is used to determine that how two layers are blended with each other. This concept is practically available in a software Adobe Illustrator, where image can be divided in different types of layers and then these layers are combined together to form a new image. So dear students, you have listened that a frame buffer is a collection of many small buffers which are used to store the pixel values of an object on the image, representing its depth, its shadows, its blending and display, etc. For a rendering pipeline process, we need to describe certain functionality for an object to be represented on an image. These functionalities plays an important role in representing the object on the image, and their variation changes the appearance of the object on the image. These functionalities are: number one, resolving visibility. It is a crucial phenomena that is an integral part of the interaction of light with the environment. The visibility algorithms aim to determine which lines or surfaces are visible in a synthesized image of a 3D scene. Number two important functionality is evaluating a lighting model. This concept has already been discussed in the previous lectures. Also, we have already discussed computing shadows and applying textures. In the previous lectures, so there is no need to discuss them further in this lecture. Here we will discuss the four main stages of rendering pipeline. Number one stage is vertex processing geometric stage or vertex shader. In this stage, we will perform task, process all vertices independently in the same way. All these vertices are also known as points or pixels. And number two, perform transformations per vertex, per pixel, per point, and computes lighting per vertex, per point, and per pixel. Number two stage in the rendering pipeline is geometry shader, which is used to generate, modifies, and discard the primitives. As we already know, the primitives in computer graphics are lines, polygons, triangles, etc. Number three important stage in rendering pipeline is primitive assembly and rasterization, also called rasterization stage, in which we will assemble or complete the primitives such as points, lines, and triangles. Then converts the primitives into a raster image, that is, into a 2D image. Then generates fragments or pixel candidates. In computer graphics, a fragment is the data necessary to generate the single pixel's worth of drawing primitive in the frame buffer. This data may include raster position, depth, interpolated attributes including color, texture, coordinates, etc. The final stage of the rendering pipeline is fragment processing or fragment shader, which means to process all fragments independently in the same way. And also it is necessary to process the fragment in order to discard or store in the frame buffer. This is how the main stages of the rendering pipeline works together to convert 3D scene into 2D image, that is 2D screen image. Dear students, here you can see that the main stages of the rendering pipeline are pictorially represented in the figure showing at the right side of the slide. The 6 blocks represents the 6 major steps of the rendering pipeline and connected with the help of arrows. The arrows are captioned, showing the output of the one stage, which further become input for the next stage, and so on. The first blocks shows various types of vertices or points in yellow, red, green, black, etc. The second blocks show transform vertices, which reflect that vertex positions are transformed. This transformation is used to connect the vertices using the connectivity information, that is line and triangle. As you can see in the rightmost block of the figure, red and yellow vertices form a line, while green, black, and cyan form a triangle. After this, the rasterization process is started, which is used to compute pixel positions affected by a primitive in order to generate fragments. Then on these fragments, interpolation is applied to color the vertices or points, which you can see on color fragments block. And to end this rendering pipeline, fragment is discarded or used to update the pixel information in the frame buffer, in which more than one fragments can be processed for per pixel position. So finally, dear student, here is the main flow diagram of a rendering pipeline comprising of the main stages, which is used to render 3D scene image into 2D screen image. The main steps of the flow diagram are vertex transformation, then vertices are become the input of primitive assembly and rasterization. Then interpolated fragments are given to fragment texturing and coloring. And finally, the raster operation is applied to convert all into pixels in order to display them on the screen of our various digital devices. Dear students, this is all about rendering pipeline or graphics pipeline, which is very important in computer graphics to display 3D scenes into 2D images on the screen. Next, we will discuss in detail the vertex processing. So stay tuned.